Okay, thank you very much. It's a pleasure for me to present this seminar where we have two invited, Professor Gunther Uhlmann and Professor François de la Rue. And first, we start with Professor Gunther Uhlmann, and the chairman is Felipe Chavez. Then Felipe.
Thank you, Mauricio. Good afternoon, everybody. It's a pleasure to be here this afternoon in this wonderful evening of mathematics. We have the pleasure to have Professor Gunther Uhlmann here with us. Gunther is a very well-known mathematician, applied mathematician, and he's studied undergraduate in Chile, then moved to the US to do the PhD at MIT, and where he has been since then. So he's a professor of applied mathematics at the University of Washington, and also has a position at the Hong Kong University of Science and Technology. And Professor Gunther is a broad mathematician, so he has been working in a lot of different topics throughout his career. So mainly inverse problems and mathematical analysis and partial differential equations. So I invite you all to check his website, where you can see many topics where he has been working on, interesting topics, very applied. And also he has several prizes and awards. So the list is long, so I won't be specific, but it's a very honor to us, Professor Gunther, and I will let you do the talk as you wish, in English or Spanish, what is best for you. So thank you very much, Professor.
Okay, thank you, Felipe, for the introduction, and thank you for coming and for the invitation. So we'll talk about an inverse problem called the Calderon Inverse Problem. So the question is, can one determine the electrical conductivity of a domain, of a medium called gamma, by making voltage and current measurements at the boundary? So one puts electrodes around the boundary and tries to infer the conductivity. Conductivity is the inverse of the resistivity, determines how much current goes from one place to the other. Different mediums have different conductivities. For instance, blood is very highly conducting, water in general. So it's called Calderon's problem because Calderon proposed it in the mathematical literature, although it has been around in geophysics for a long time. In fact, the Schlangberger company of oil prospecting was started using electrical methods to find oil. I'll talk a little bit more about that in a minute. So Calderon was an engineer, but it was no mathematical career per se at that time in Argentina. It also has been proposed for early breast cancer detection because normal breast tissue has a very different conductivity than cancerous breast tumor. The reason is that cancerous tumor in general needs blood to grow. As I mentioned before, blood is very highly conducting. So one can see the difference between the tumor and the normal tissue. It is Calderon, one of the famous analysts of the 20th century. And he said something very interesting when he accepted the Doctor Honoris Causa of the Universidad Autónoma de Madrid. Says, I translated from Spanish, my work at Yacimientos Petrolíferos Fiscales, YPF, this is the oil company of Argentina, still exists, was very interesting, but I was not well treated. Otherwise, I would have stayed there. It was a great fortune for mathematics that Calderon did not have a good time at YPF. So this is a cartoon of the oil prospecting using electrical methods. And this is called an oil well. You put electrodes around, and one tries by putting voltage and measuring the induced current flux. One attempts to find oil. The reason why this is useful, because oil has very different conductivity than the surrounding rock. And for breast cancer detection, LD cancer detection as a screening method. Nowadays, X-ray mammography is the standard method, but X-ray mammography takes very few X-rays and misses cancers. And also for soft tissues, the X-ray attenuation is almost the same as cancerous. So electrical measures might be useful because, again, as I mentioned earlier, the tumor has much higher conductivity. So you put electrodes on one side of the breast, you input voltage, and you measure the induced current flux. More recent application has been proposed to detect whether when you have a stroke, whether it's a clot, that means the blood doesn't go through, there's very low conductivity, or when there is an hemorrhage, a burst of the veins or arteries, and this is very high conductivity because of the blood, but the symptoms are the same in both places. And we have developed methods to be able to detect quickly. This is, I should say, mathematical method at the moment. It's not experimental. And you can see the simulations here. This is very high conductivity. You can see it, and very low conductivity in this particular case. The idea is to try to use a method that is simple, portable, and can detect quickly which one are you having, a clot or a hemorrhage. Say at an ambulance, an emergency ambulance, for instance. This is similar to what is done in X-rays. You can see it's measuring the electrical conductivity. In the left is uniform conductivity, is low conductivity in the middle, and then high conductivity in the right. In Brazil, where I think this conference takes place, I understand, this has been used in hospital. And this is the machine. And the advantages of electrical impedance tomography is non-invasive, is safe, you don't use radiation, as opposed to CT scans or X-rays. It's portable, so can be put in different beds of hospitals. It can be used to monitor continuously the functioning, for instance, of the lungs. And no known issues are known, it's used for long periods. And this, again, in this hospital in Brazil, has been used to monitor the ventilation of COVID patients. How are the lungs functioning? Because we can see the lung is functioning by inputting blood, and then the blood goes out. So let me describe the mathematical problem. So by Ohm's law, the current is given by the times resistivity is the change in the current. Remember, the conductivity is the inverse of resistivity. The conductivity can be isotropic, scalar, or anisotropic, the symmetric value. This is the case, for instance, of muscle tissue, has the different conductivities in different directions. If there are no sources or sinks of current, the divergence of the current is equal to 0. And this is very simple partial differential equation. It's elliptic. For instance, when gamma is equal to 1, conductivity 1, uniform, the divergence of the gradient is a Laplacian. So this will be harmonic function. And the conductivity is assumed to be positive, and you input a voltage potential on the boundary, and the current flux at the boundary is the normal component of the current. So mu is the unit outer normal. And the information is encoded in the map, that sends the voltage potential on the boundary to the induced current flux at the boundary. And the Calderon Inverse Problem is also called electrical impedance tomography, also resistivity impedance tomography. Thus, knowledge of this map determines the conductivity. Of course, this is an idealized situation. In practice, you have only finite number of electrodes around the body, and then you make my finite number of measurements. But the idea is to solve this problem and then approximate. You have a finite number. In the mathematical literature, this is called the Dirichlet-Neumann map, because your mapping was called Dirichlet data to Neumann data. Let me mention another feature, which is that this is a nonlinear problem, because U depends on gamma. How it depends on gamma is a crucial problem that we have in inverse problems, because we don't just want existence and uniqueness and regularity of the solutions. We want to know more precisely how the solution depends on the coefficients. So for the question of uniqueness, which is the basic question about this map, whether you have two Dirichlet-Neumann maps giving the same information, the conductivities are the same. This was solved a long time ago by Sylvester and myself for C2 conductivities, continuous two derivatives, and has been extended to several situations. Let me mention the last two ones. This is one derivative in Ln. N is the dimension, and this was proved by Hannerman in 2015. And a nice result by Caro and Rogers showed that the uniqueness holds for Lipschitz conductivities, one derivative in L infinity. The conjecture is that this W1N is optimal for uniqueness, although there is no counterexample at the moment. It is believed that one derivative is necessary for uniqueness in general, because unique continuation from the boundary is valid when you have only one derivative. However, it's also my personal conjecture that uniqueness should be true for piecewise smooth conductivities, because those are realistic situations. The counterexamples are likely to be very strange. And a reconstruction method was developed using the ideas from uniqueness by Nachman, and stability, meaning is two Dirichlet-Neumann maps are close in some sense, where the conductivities are close. And numerical methods, that means finite number of measurements, are developed by many authors based again on this, on the mathematical ideas using the uniqueness proof. So what is the basic idea for all the uniqueness proof that I mentioned here? Is a reduction to the Schrödinger equation. You make this transformation, and then the question for you now is the Schrödinger equation, Laplacian mass potential that appears in quantum mechanics, for instance. You put minus lambda squared, but this potential is encodes that too. But the potential in this particular case is Laplacian of square root of gamma over the square root of gamma. So that's why you need some regularity on the conductivity for uniqueness because of this reduction. You lose immediately two derivatives. So that was the reason of C2 for the starting result. Then Q is just L infinity. But you can also consider the inverse problem, which is related to inverse scattering for a potential, for more general potential, not necessarily this type of potentials, by defining the Dirichlet-Neumann map to be just a normal derivative at the boundary. And there is a very simple identity, which is integration by parts. It's just Green's formula, which relays the information on the potential to the information on the boundary, which is the Dirichlet-Neumann map. So the difference of the potentials times the product of solutions of different equations gives you information on the boundary of the difference of the Dirichlet-Neumann map. So this is linear in Q, the difference of the Q here. The nonlinearity appears in U1 depends on Q1, U2 depends on Q2. For instance, for uniqueness, you want to show that is lambda Q1 equal to lambda Q2, then Q1 equal to Q2. And for stability, if these maps are closed, then you want to show that the potentials are close. And for reconstruction, you can take Q2 a non-potential, for instance, 0, and you try to reconstruct the potential Q from lambda Q. But in any one of these cases, you want to find many solutions of the equation. But this is an elliptic equation. So how to find solutions? That's the crux of the matter. And then these are called complex geometrical optics solutions. You take a complex vector as a real and imaginary part, so that rho is equal to 0. That means that the length of the real part is equal to the length of the imaginary part, and they are perpendicular to each other. And for rho sufficiently large, there are solutions of the equation that behaves like these exponentials. These are where exponentials considered by Calderon. In fact, Calderon looked at the linearized problem at conductivity 1 or constant, and this is the Laplacian. This Laplacian of these exponentials is 0 because rho dot rho is equal to 0. So this says that there are solutions of the Schrödinger equation that behave like these exponentials for large complex frequency. So this goes to 0. And how it goes to 0 depends on the regularity of the potential. If the potential is L infinity, this is in the L2 norm. So these type of solutions are what are waves for elliptic equations. In general, elliptic equations don't have waves, but this is the analog. You probe the medium with this type of solutions. How do you use this? For instance, for uniqueness, in similar ways, you use it for stability and reconstruction. You take two of these solutions with different frequencies in dimension 3, you fix a vector k, and then you have you take two vectors perpendicular, and so that the length of the vector eta can be found by the length of k and l in order for rho dot rho to be 0. And then you plug it in, the real parts cancel out. That's the reason to choose it this way. The L is an extra vector because we're in dimension 3. And then when you multiply, you get this phase. But this goes to 0 if L is large, because rho goes to infinity. And then this goes to 0 in the L2 norm. So you get that the Fourier transform of Q1 minus Q2 times the characteristic function of omega is 0. Therefore, Q1 equal to Q2. So that's the idea of the uniqueness proof. And that has been the same idea for all the other regularity theorems that I mentioned. The difference is on the how this goes to 0, how the lower order terms go to 0. So, so this is what we have shown, that if you take a harmonic function, there is a U here, lambda, the Dirichlet-Neumann map determines Q. In electrical impedance tomography, the application is that the Dirichlet-Neumann map for a conductivity determines the conductivity. There is another method, related method called optical tomography, which instead of applying currents, which are low frequency, you take a laser beam for light, and you probe the medium with light. And the equation is very similar, but the physical application is different. The U is now the density of photons. This is called the diffusion coefficient, and sigma A is the optical absorption. The different medium have different optical absorption, different diffusion coefficient, and omega is the frequency of the light. If omega is not 0, then you can recover both coefficients, because you can recover complex Q here, not necessarily real. So you recover this is real, the real and imaginary part. You can recover both. If omega is equal to 0, then you can recover one of them, either D or sigma A. And optical tomography is also used in hospital to monitor the brain, the functioning of the brain of premature babies. The reason one chooses a small medium is because light gets very scattered as you go inside the body. Because this is less scattering, and it's an effective way to have a continuous monitoring of the functioning of the brain. So let me mention the anisotropic case. As I said before, muscle tissue is very anisotropic. The conductivity is different in different directions. And this is modeled by a positive definite symmetric matrix. And the equation is the same, divergence gamma gradient U, but is written in this form. And the measurement, the induced current flux, is to recover the normal component, which in this case is given in this form. Mu I are the components of the unit outer normal. This is a vector. Calderon problem in this case, can you recover the conductivity from the Dirichlet-Neumann map? And the answer is no, in general. There is an invariance here. If you take the equation, the same equation as before, you take something which is called the push forward of the conductivity. It gives you exactly the same observation where psi is any change of variables, there is identity on the boundary. Any diffeomorphism, which is the identity of the boundary. What is the push forward in terms of matrices? Is the Jacobian transpose composed with gamma composed with the Jacobian divided by the model of the determinant. And this can be seen by just changing variables in the equation. You can easily check this invariance. This is an infinite dimensional group of diffeomorphisms that leaves the boundary fixed. Any rotation, for instance, inside, gives rise to a new conductivity that gives the same measurement. And it's because this equation is invariant at the changes of coordinates. And an open problem in general is the only obstruction. Because if we know that this is the only obstruction, you know some a priori information about the conductivity. that will give you, that maybe fix the exchange of variables that you're using. For instance, if gamma is isotropic, a scalar, and psi star is isotropic, which is the case we had before, then psi must be the identity. So depending on what you know a priori about the conductivity, you might be able to determine, but we have to know that this is the only abstraction. And this is for the people who are interested in geometry, this is a geometric problem, can be formulated for Riemannian manifolds, compact Riemannian manifold with boundary. This is called the Laplace-Beltrami operator, and the Dirichlet-Neumann map is given in this form. So the question is, you can recover the metric inside by making measurements outside. It's like holography. Can we recover two-dimensional information? Can we recover three-dimensional information inside from 2 dimensions? The conductivity is related to the metric by just the square root of the determinant. The G upper ij is the notation for the inverse of the metric G. So it's the same problem. It's a geometric formulation. And the only result, a general result known, there are some more specific things, is the case of real analytic metrics, conductivities or metrics. You can assume that the Dirichlet-Neumann maps are the same, even measuring any open subset of the boundary for any function supported in that open set, can be the whole boundary. This is called partial data. Then there exists a change of variables, which is the identity where you're making the measurements. So that one metric is the pullback of the other. The pullback is the inverse of the push forward. And you can recover the topology also. I mean, you just need to know the boundary and the Dirichlet-Neumann map. This is information on the boundary, and you can recover the manifold itself. But this is again under the assumption of real analyticity. As I mentioned before, it's an open problem where this is true for smooth metrics. It's one of the most interesting open problems in Calderon's problem, in my opinion. And new ideas are needed here. Okay, so let me describe briefly extensions of these ideas to nonlinear elliptic equations. And in fact, one can solve problems for nonlinear elliptic equations that one cannot solve for the linear case. So it's already observed for the wave equation and the parabolic equations, and in the elliptic case in these papers. For the conductivity equation, nonlinear conductivity, there are many conductivities that are not depend on X, but on the current itself and the potential. For instance, gamma depends on X and U. It can be anisotropic. Gamma depends on X on gradient of U, or gamma depends on U on gradient U. I will consider now a more general case, but first let me talk about a simple semilinear equation, elliptic. For instance, something like this, Q of X times the power. And we can show that for a small enough f, there exists a unique solution of this equation. So here m is bigger or equal than 2. That means there is a nonlinearity. It's u squared. At least u squared can be higher order than nonlinearity. So the solution is denoted by uf, dependent on f. And partial data here, I mentioned briefly before, means the following, that you take the support of the Dirichlet data in some open set, and you're measuring, some on gamma 1, and you measure it on the other open set. Can be the same, that's the most interesting case, in fact. Can be disjoint, can be have intersection. And in this case, one can prove a result that is not known for the linear case. When you have just Q of X, it's not known. This uniqueness result, there is also stability and reconstruction result, but let me just mention uniqueness. That you can recover the potential uniquely by making measurements just on this open set that can be as small as you want. And you can consider more general potentials as long as this has a power series expansion in U, not in X, in U, and the U square, U cube, a combination of all of this. There is no linear term. Again, I repeat, the situation is not known for the linear problem. So the nonlinearity helps. And this is the result in more general terms. And what is the idea? Let me just mention it in the case, the idea of the proof. The same idea is true in more general nonlinearities. But let's take a quadratic nonlinearity, which is the simple case. Now you take two parameters. So we do what's called a second order linearization. And then we know that there is a unique solution, and we differentiate, this is the second order linearization with respect to these small parameters at 0. And uj at 0 is 0, because we have no linear term, no potential term. And then you obtain, similar to what we had before, Q1 minus Q2 is orthogonal to product of 3 solutions. But these are harmonic now, not solutions of the Q1 of Q2. They're harmonic functions with the support contained in the open set where the Dirichlet data has support. And you take V3 non-zero. And there is a theorem that says that the span of harmonic functions that vanish outside a set gamma 1 is dense. So this is going to be, this is non-zero, this is dense, so Q1 minus Q2 is orthogonal to every function, and therefore Q1 must be equal to Q2. So this is the power of higher order linearization, that you're linearizing around, in this case, the 0 potential, which is just harmonic functions, and you need some condition of density for harmonic functions, which is easier to prove. And then using similar ideas, here you need to do multiple linearizations for a conductivity, a quasi-linear conductivity that depends on U and gradient of U. In this case, you can define the Dirichlet-Neumann map in the same way. And then this result is that you can recover the conductivity uniquely in that case. Also, there is stability and so on, stability results and so on. Okay, so the last topic I want to mention is the Calderon type problems for the fractional Laplacian. This is a non-local operator that models in many situations non-local interactions. This is usually defined via the Fourier transform. You take the inverse Fourier transform, the Fourier transform of this applied to function f is modulo c to the 2s times the Fourier transform, the inverse Fourier transform. So this is a convolution. It's a singular integral or a pseudo-differential operator, but it's not local, does not preserve support. So computing this involves values of U far away from X. And the fractional Laplacian appears in steady state for many, for this type of situation, super diffusion. It's also Levy flights, when you have jumping processes. The normal diffusion is the usual heat equation. And subdiffusion is in the case you have fractional in the time derivative. So the fractional Laplacian is related to anomalous diffusion involving long-range interactions, because this involves long-range interactions, jumping Levy processes, improbability, financial modeling with jump processes, and so on. So what is the problem in this case? We cannot give directly data and Neumann data, because the solution will be singular at the boundary, but we can give exterior data. So this problem is well posed. Omega E denotes the exterior domain. And then the Dirichlet to Neumann map, the S is between 0 and 1 here. It's always fractional. And maps HS to the H minus S is just given by the fractional Laplacian applied to the exterior. But you can also, of course, give data supported in an open subset of the exterior as small as you want, as close as you want to the boundary, and the same for this. And the inverse problem is, can you recover Q knowing the Dirichlet to Neumann map? And the result is indeed the case. And you can take arbitrary open subsets. This is the partial data case of the exterior, as small as you want. And you measure the Dirichlet to Neumann map in one of the open sets for data supported in the other one. Then the potentials are the same. And this is true for arbitrary potentials. And the same mechanism is true for all dimensions. I only talk about dimension 3 or higher before, but the dimension 2 has to be treated differently. And this gives a new mechanism for solving non-local inverse problems. And the key difference, so then the non-locality in fact helps. This type of results, again, are not known for the linear case, partial data type problems, in dimension 3 or higher in particular. And the key thing is that, which is not true for the standard Laplacian, is you have U restricted to an open set, and the Laplacian, fractional Laplacian restricted to the open set is 0, then U must be 0. This is not true for the Laplacian, because if you take, you can have a non-zero function, compactly supported function. Outside the support, U is 0 and the Laplacian is 0, but the function is not 0. And the proof uses the famous Caffarelli-Silvestre extension, which can relate the fractional Laplacian to the Dirichlet to Neumann map for a degenerate elliptic equation, except when S is equal to 1/2. S equal to 1/2, you get the standard Laplacian here. So the fractional Laplacian is obtained from a local equation, but it's degenerate in one more dimension. So you add one more variable. The fractional Laplacian is related again to the normal derivative. In the case S equal to 1/2 is the normal derivative. And then one uses Calderon estimates proven by Uhlmann, and that this fact to show the uniqueness. But this is the reduction that has been used in many non-local problems, also non-local inverse problems. And this allows us to prove the following result, that any L2 function can be approximated by solutions of the non-local equation. Okay. And then, for instance, so if the non-local Dirichlet to Neumann maps are the same, the identities are the same. This can be proven using Fourier transform, for instance. And now we don't need to construct new solutions because this can be approximated by one. U2 can be approximated, and U1 can be approximated by solutions. U1 can be approximated by any function can be approximated by solutions. So this is orthogonal to any solution. Therefore, Q1 must be equal to Q2. So this approximation result also is not true for harmonic functions because harmonic functions are not dense, certainly not dense in L2. Okay, so since I'm not running out of time, let me just finish. One can consider also anisotropic problems, and this has been also solved when we don't know the corresponding result for the linear case. I don't have time to talk about this, but there are many other results in recent years, as this is a very active field, and then one may consider more general non-local operator rather than the fractional Laplacian. And I finish with this. Thank you.
Thank you very much, Professor Gunther. Now we open the mic for questions, comments, and anything else people want to say. It's very interesting talk, so the chat is open, and you can write in the chat your questions, or even write, and then I can read the question in either in Spanish, Portuguese, or English, so as you wish. So let me, or you can use the chat, the mic. Okay, Professor, I have actually a very naive question maybe. So in the applications, I think it's slide 18 that when you introduce the parameter omega, then I think it's in the first part of the talk, then you said that if omega was different from 0, you could recover both d and sigma. I think it's slide 18. I just if you can say, and then if omega was 0, you could not recover both at the same time, I think. And I wonder if there is a physical explanation for that.
Yeah.
Like what?
Yeah.
18, I think it's slide 18.
Yeah, it was later, right? Yeah. This.
Yes, there. Yeah, 18.
Yeah.
Yes,
So,
yeah.
so the result is that from the Dirichlet-Neumann map, these measurements on the boundary, you can recover the potential. This potential can be complex. It can have a real and imaginary part. So in this particular case, D is a diffusion approximation is a real is a symmetric matrix, or let's say a scalar, right? So you reduce it to a potential that has real part and imaginary part. Right?
Okay.
Because this is I omega.
So the AI is also important.
Right. If omega is 0, you can reduce it to a potential, but the potential has two parts: d, the Laplacian of square root of d divided by the square root of d, and sigma a, and you cannot separate them. But in the other case, you can.
I see. I have another question, which is I believe it's actually related to this because you can separate in real. So, Professor, what is it? Are there any references for instance, systems of elliptic equations? For instance, you have two equations and coupled, and then you want to recover a potential which is in one of them.
Yes. In fact, I didn't have time to mention all the applications. One example is the Maxwell equations. So you can recover, because you can reduce it, Maxwell equations, that's exactly what you said, the Laplacian for an 8 by 8 is Laplacian times identity 8 by 8, and a potential Q which is 8 by 8. And then you can recover all the electromagnetic parameters, the electric permittivity, the magnetic permeability, and the conductivity by making measurements on the boundary. So Maxwell equations is an example where you can. Another one is the Dirac equation, which is a system. One system for which it has not been done is elasticity. For elasticity, there are isotropic elasticity. There are two parameters, the Lamé parameters, lambda and mu. It's known that you can recover one of them and the other one if it is small. But it's an open problem whether you can recover both. So this will be an interesting question for systems.
I see. Thank you very much. So, any question? Pregunta pessoal. Se alguém tem alguma pergunta, se alguém quiere perguntar algo, puedes usar el micrófono o escribir en el chat que lo traducimos, si eso. Bueno, en el castellano el profesor Gunther también lo puede leer, así que tranquilos. Perguntas, pessoal, se vocês quiserem escrever aí no chat ou falar no microfone, podem fazer. So, okay, I think the talk was very informative and clear. That's why we don't have many questions. But Professor, just one last question. Maybe can you give us some good reference for students, because most of people here are students. So who wants to start on reading about Calderon problem? Or...
Yeah, I have a survey paper. Have a couple of survey papers that I can. Then you can look at the references in the survey papers. Okay. I can. If somebody sends me an email, I can send them to you.
Perfect.
Yeah.
Thank you.
And there is a book. There is a book in progress. Hopefully, it will be finished this year.
Even better. Okay. Thank you very much.
Thanks.
So since we don't have questions nor comments, so let's thank Professor Gunther. It was a pleasure. Very, very nice talk.
Thank you.
We learned a lot, and thank you very much, Professor. And
thank you for the invitation.
Hope we can have all a next talk by you, and maybe in person where we can all meet. Okay.
Yeah, and I would love to. Thank you.
Thank you very much, Professor.
Bye.
So, Mauricio, creo que se puede acabar la grabación, ¿no?